Hi there, and welcome to insideQuantum, the podcast telling the human stories behind the latest developments in quantum technologies. I'm Dr. Stephen Thompson, and as usual, I'll be your host for this episode. In previous episodes, we've talked a bit about quantum information and quantum computers. We've spoken with researchers working on learning theory and quantum error correction, with a focus on how near-term quantum computing hardware can be put to use. Today, though, we're going to leave quantum computers behind and see how techniques initially developed for quantum information can be put to use, shedding light on some of the most enigmatic objects in the universe. It's a pleasure to be joined by Dr. Monica Kang of the California Institute of Technology, a researcher in high-energy physics. Hi, Monica. Thank you so much for joining us here today.
Well, thanks for inviting me.
So before we get onto the topic of black holes, which I'm sure everyone listening is desperate to hear about, let's start slow and let's first talk a little bit about your journey to this point. So can you tell us what first got you interested in physics?
Growing up, I was actually interested in a variety of logic and reasoning on why things occur or how to understand a variety of different objects. When I was in middle school, I was really fascinated by kinematics when we first learned like basic little things. We learned first gravity in a very crude way and velocity, acceleration. It really got me very interested. So I started going to this gifted middle school program. The Korean government have these type of program where I was raised. And I developed more interest towards slightly more abstract, but at the same time, direct equations and formulas that's more crisp and concise way of describing everything.
Okay, what kind of age were you at this time?
13, 14.
Wow, that's a pretty young age to be exposed to that more kind of abstract side of reality.
To be called abstract is maybe pushing a little bit. We do some variety of very classical experiments at first. Mm-hmm. I think it was very fascinating because I had many questions on how much when you brake the car, how far it can go. And I remember asking so many questions like that to my dad. And seeing how you can make lights to focus better and burn, and like describing that as energy, I think it really motivated me to learn more about it. I guess it got me here now. So that gifted program did something good.
So after the program then, where did you go afterwards?
I went to Korea Science Academy. It was at the time the only national high school that admitted for people directly more interested in math and science. Well, by the time I got in, I was more open-minded. Of course, I didn't know that I'm going to be a theoretical physicist. No way. But by that time, I had a more sane reasoning that math and science sounds like a good thing to learn at the time. Mm-hmm. It could be good to be a math or science type of person, engineering all included. Whereas engineering is very strong in Korea, so I, of course, had that mind as well. But not limited to it. It's not prohibited that we go to other type of fields as well, necessarily. Just more focused to go to a more STEM type of field.
Right, I see.
And that looked right to me. I liked history, but I didn't like how it was presented. I also like art, but doing that as job sound very difficult.
I guess risky as well.
True, but I was young. Risk may not have been the first thing that came to my mind. It was just that I couldn't imagine myself playing violin every single day for more than 8 hours a day.
Are you also a violinist then?
I play some violin, yes.
Ah, that's interesting. We had a previous guest who also plays violin, and we remarked at the time that there seems to be a lot of overlap between physicists and musicians.
I think it's because it demonstrates symmetry and elegance, just different language. One is more concise and the other one is more expressive. I don't know. I really think they are really about understanding our life and where the universe comes down to in the end.
That's true and very poetic.
Oh, I like that. Yeah, I also was dancing. I mean, I was a child with many interests. It's just that it looked more right to me at the time. Might as well, it's a good thing to learn, right, as a kid. So I went to that, and that school comes with a very specific tracks that you can follow, and I did more of a physics math type of track, and I guess I continued doing physics. Cool enough. So that high school definitely did something right too.
So then when you went to university to study physics, did you have any idea what type of fields you would want to go into, or were you still just interested in as much of physics as you could possibly learn?
I had no idea what I want to do necessarily. I remember, so I had the luxury of to do some research when I was in high school. That high school was wonderful in that way. I tried some number theory and type of research. Well, more correctly, it's like rings and abstract algebra based, and you do more number theoretic analysis to it, and that was very fun, but I felt like I was missing something. I also had another year doing soft matter experiment / theory, like in between you do some coding and actually you do research. It was about ferroelasticity, which was very interesting.
Yeah, wow.
That was very fun. I think that really got me interested in more condensed matter aspect. And I want to do something different as well. So I did try more quantum-y, but still kind of ultrasonic wave and using that to understand like more material-focused part of condensed matter type of research. But I also had a pleasure to take the science, philosophy, and history type of course that was offered in my high school. It was taught by a particle physicist. He was a theorist. And it was very fascinating to learn about the beginning of the universe. I mean, of course, we all read The Elegant Universe, and that book is also wonderful. And it got me really thinking, string theory could be such a cool thing to learn. But I wasn't like determined on anything. I definitely did not even know that I would for sure be a physicist. I just thought it would be good to learn more. So I went to college and did math and physics.
And you've ended up now working in the field of high energy physics.
That's right.
This is a little bit different to the previous guests that we've had on, where we focus more on sort of quantum information and quantum technologies in a way that is perhaps more familiar to people. For any listeners who are maybe not familiar with what high energy physics is, can you give us a brief explanation of what the field is? I know that's a big question. What the field is and what types of things that you're interested in?
So high energy physics is about energy at more higher level scale. One very classical scale, we know just basic Newtonian gravity, and that's what we can see. And from that, to understand better with the space-time was general relativity, which, granted, it's not high energy scale, but somehow it's part of high energy physics because we are interested in space-time based physics. But that being aside, the other forces that I'm sure all the physicists learn when they're very little, like strong force, weak force, and electromagnetics, they can be combined and put it into a formalism that even led to the Standard Model, and these are much stronger than that of gravity in like certain in the middle scale, but it becomes now all four forces are very big in high scale. So high energy physics is more understanding physics when the energy scale is quite high. And we take the language of quantum field theory to describe these physics, and the first thing that it was really useful for is to develop the Standard Model, which led to Higgs boson discovery by experimentalists in high energy physics. So these are the vibes that we understand to describe the world. Of course, it would be great to write down as an action that describe all the kinematics of every particle in the universe and ourselves, but of course we're not there yet. In any way, I don't know, it will be eventually be working. I have no idea. But those are the feel of our area, I would say.
So it's really almost the opposite regime to where people working on quantum computers are coming from. So, for example, I guess I'm not really someone who works on quantum computers either. I do many body theory. But for us, we're often very concerned with the low temperature physics, the low energy behavior of a quantum system, and just trying to understand basically if you take this very cold quantum system and you add some small perturbation, how does it behave? But you're at the complete other scale, right? You're working with space-time, you're working with large structures, with high energies. And at first sight, these two fields feel like they're completely separate, right? They look, to me at least, like there should be no direct connection between the two at all. And I imagine people are probably wondering, okay, why on a podcast focusing on quantum technologies, why are we talking to someone from the high energy field? So can you tell us a bit about some of your work on connecting these sorts of quantum computation, quantum information concepts with the high energy field that at first sight looks so different?
Right. So think of it this way. So we have the universe, and you want to understand in every possible way. And I was saying that we take quantum field theory as a language to take to describe anything. But we can probably try to understand where the regime is kind of semi-classical, in the sense that gravity is still fixed as a metric. Like, in a way, the gravity is there, and all the rest of the particles are fully quantum interacting.
Okay.
So it's like a semi-classical setting to understand our bulk, but it's quantum interaction, so it's quantum mechanics still intact. And to try to explain that, it's like a borrowed concept of the quantum field theory. At first was Weightman axiom, which led to Riesz-Leiter theorem. That I think it's also familiar to quantum information theorists for a lot of them. It says that you act on some operators in the open region of the spacetime, like some open region, let's say, then you act with all the operators onto the vacuum. Then it creates the whole different type of states, right? And those states will then form to be still dense Hilbert space in that region, meaning that there will be ridiculous amount of entanglement that can be present. And that in quantum field theory, entanglement is unavoidable. Now, entanglement entropy really sounds like it's more information theoretic type of object. Of course, in universe, we can measure many things. It'll contain many different informations. And information encodes our matters. By matters, I mean like all the particles in the universe and everything. So in that way that we're having interacting entanglement as a fundamental quantity we can look at to encode these information, and it brings up another viewpoint to see and analyze the universe in that fashion.
So just as entanglement is the, I guess, the sort of natural language for these sort of low-dimensional, very quantum systems, it's also a natural language then in this high-energy field theory framework as well. So there's a commonality, I guess, hiding behind the scenes. So even though these fields look like they're very different, you find that in both of them, entanglement is a core concept that can't be avoided and is very useful. And then entanglement also implies that, sort of an information theoretic point of view, that information is really the building block of both quantum computers, quantum technology, and all this low energy stuff that we do, but is also the building block, in a sense, of the entire universe. Can I say that?
I would say that is the right interpretation, because entanglement is something we can explicitly compute, and more toolkits, the merrier. Of course, it can be approached in a variety of different contexts, but as we know, quantum field theory says that entanglement is unavoidable. It really provides another way of viewing the universe and can understand better. So in a way that we have holographic principle, it's kind of a particular manifestation of it as an ADS-CFT, that it's because physicists can only deal with things more easily when there's boundary, and NT de Sitter space has a nice closed boundary system.
So you mentioned holography and ADS-CFT. Can you maybe explain a bit about the general idea of what holography is and what ADS-CFT actually means, why it's such a core and important concept?
That really brings down to our interest about the black hole. So black hole is the reason why high energy physics is particularly interesting in understanding more of the universe, because, well, we have a black hole and we are living an exciting phase that Event Horizon Telescope even measured the black hole in our own universe not so long ago.
Exactly. I think at the time of recording that was only maybe two weeks ago, something like that.
Yeah.
So yeah, very recent new development.
It's really fascinating. You see that ring and be like, wow, that's so amazing. The black hole is a very fascinating object. It's where gravity is strong. Of course, that's why it's condensed. And it's quantum mechanical at the same time. So that you really need to have quantum field theory and general relativity both at play. And to understand that object, we really need to now then have a theoretical way to describe quantum gravity. And to do that, it's very difficult, of course. And one way to think about that may be using this information. So the black hole, let's say, on the area, so that's a horizon, event horizon. And Hawking discovered that the black hole shouldn't be really black, in the sense that there will be particles that's going to be around the event horizon, and it'll cause radiation outwards, because it's a two-particle, let's say particle and antiparticle pair can go in, one goes inside and one goes outside, then it'll create radiation. So it's no longer really black in a way. So then you have this radiation coming out of the area, and that should be then encoded as the interior of this black hole. So in a way, this is already showing that the volume of the black hole is now encoded on the surface, which is like the area, the event horizon of the black hole. So looking into that, Tooft then understood, so that's going to be giving rise to explanation of the area law, meaning the entropy of the black hole is proportional to the area, not the volume. So this is why it would make sense. And it got generalized further by Lenny Susskind originally and various others later on, that it must be the fact that the volume is encoded as the area, so that any theory describing the volume is explicitly dual to a theory in the area. And you can generalize this further to always have any d-dimensional bulk theory describing the volume will be dual to a d-1 theory that's describing the surface around that volume.
And this then is the holographic principle, I guess.
That's right.
So it's connecting a theory in some number of dimensions to a theory that is, I guess, equivalent in some sense, but in a lower number of dimensions.
That's right.
So then why is this a useful concept?
It's very useful, as I was kind of using a particular term, that information is encoded. And all that matters, and entanglement is unavoidable, then the entanglement of this bulk theory and then the entanglement of the boundary theory should be in some ways dual and can be understood as not quite identical, other than just gravity dissipation as an error. But as I'm using the term as gravitational error, and then encoding, so it's like a reconstruction. So that's an explicit recovery channel that one can really use. So another way to say that is the universe in this format has a naturally arising quantum error correcting type of structure, so which it connects to quantum information theory, how it can be really utilized to understand this behavior better.
Okay, so to recap that in a way then, we're saying that black holes are interesting not just because they're kind of cool and mysterious, but they're interesting because they're a thing that if you want to understand them, you really have to have both gravitational theory and a full quantum field theory. So it's a place where, in a sense, the needs of high energy meets the toolkit developed in low energy physics.
Yeah, so it's a general relativity, which is basically gravity understanding the space-time.
Mm-hmm.
That's not quantum mechanical at the moment. And the quantum field theory is fully quantum mechanical. So you're putting both pictures together. Mm-hmm. Now, that's why quantum gravity.
So there's one thing you said in there that I think I have to follow up on. I think you said something in there about black holes and error-correcting codes. And now I think anyone listening to this who's maybe listened to previous episodes about quantum error correction or has some exposure to that, they're probably wondering, how do you possibly connect a black hole to an error-correcting code? Error correction, I guess, in the simplest sense for anyone who maybe hasn't listened to the previous episodes, is the idea that
errors will creep into a computation inevitably, be it a classical computer or a quantum computer.
And you need some way to detect and fix these errors. And doing this in a quantum computer right now is still a huge field of research. There are a lot of potential ways to finding correct errors, and people are still working very hard on finding out what are the best ways for the current hardware that we have. How then does this connect to something like a black hole? Because the idea of manipulating qubits, manipulating quantum bits to detect and reverse errors, that sounds very, very different to the type of physics that you're discussing here on these high energy scales of black holes. How does this error correction somehow apply also to black holes?
Right. So let's go to then the setting of ADS-CFT. The ADS is some anti-de Sitter space bulk, right? It can contain black hole, for sure. Will be on the boundary is just pure theory as a field theory. It's not having any gravity at all, which will then arise as a gauge theory in that context. And it will be then giving you as a thermalized state. Okay. So that with this correspondence that we can, first of all, look into more easier perspective. Of course, area is easier than the volume. Gravity is generally harder than the quantum field theory. Of course, there are some reverse settings that we can utilize, but this is more of a scope that can be easily understood. So we're really using the boundaries perspective to know more about gravity bulk.
So the idea then, if I understood that right, is that the theory on the boundary does not have gravity. Gravity doesn't appear in the boundary theory. So then this is a way of taking this is probably an oversimplified approach, but you're taking the hard gravity problem in some number of dimensions, and you're mapping this onto an equivalent problem that doesn't have gravity in one dimension lower, which yes, naively sounds like it should be simpler, but it's still a strongly quantum mechanical problem. And because we know that these two theories have to encode some of the same basic properties, and I guess in particular the sort of information theoretic properties, this means we can take this really complex gravity theory, we can rewrite it in terms of a lower dimensional theory without gravity that has the same information properties. And by studying these information properties of this low dimensional quantum theory, we also learn something about the gravity theory at the same time. That's the idea.
Correct.
Great.
I think that's why it's really exciting. Also, that you can naturally then think of a setting that you can have a quantum channel from the bulk to boundary. That's going to be like a explicit unital and understandable quantum channel. And you can then maybe have recovery channel that'll emerge back as a holographic map back to the gravity. And that type of perspective is particularly naturally utilized in the context of quantum information. So it can be now more seen that it will be easier to analyze that way.
Okay, I see. And then let's come back to error correction. Where does error correction come into this?
Well, ADS bulk to boundary, as I was telling you, that it can be giving you as a quantum channels and recovery channels and all that. That recovery channel to exist, to recreate then boundary to the bulk, that would be then bulk reconstruction from the boundary. And that is a natural thing that we would expect to occur. That brings as an ADS CFT dictionary to understand this duality, and that then naturally we have this type of protocol built in to understand the universe a little bit. But there's gravity, which is not making it exactly all recoverable precisely. Another way of saying that is gravity is giving you and erasing a term that's more of an error and has to dissipate away.
Oh, I see.
So
Okay.
in a way of saying that universe is not a very good quantum error correcting code.
So gravity arises like an error. That's an interesting perspective.
Right.
It's really incredible that error correction, something that was designed to improve quantum hardware, something that was designed by people to improve an architecture also designed by people, somehow is emerging in this completely different regime entirely, and that it's useful, that it works. It's possible. It's kind of mind-blowing to think that these two different regimes can be linked by some core concepts, and particularly something like error correction, which always feels to me like an invention by people, not a sort of fundamental property of the universe. But essentially what you're saying here is that it is, in a sense, a fundamental property of the universe. It really is built into space-time.
I don't know. I think we always see in the beginning when you're developing toolkits, maybe it wasn't so useful in all the other areas, but it turned out to be. It's really interesting that this is how it works.
So do you think then that is information really the fundamental building block of the universe? I know that's a very big question, but it seems to be a point of view that's unifying a lot of different things, partly within quantum computers and quantum technology, but also, as we've heard, unifying these low energy physics with some of the high energy physics. Is quantum information the theory of everything? I'm sorry to put you on the spot.
I don't know. My answer is I don't know. But information is something that contains all the matters and variety of things one can do. And understanding how information transcribed is not just about algorithms or quantum computers. It's just that when you even move an object, just information is removed and transferred. So maybe it depends on how you think about information as a overall thing. It's not an object, right? Just physically some quantity of some kind. So what type of object you pick up to be and what are things that you describe it as, fundamentally as a physicist, you need to understand better. In a way, when we had relativity, light cone was naturally the bound as a speed of light. As a physicist, that's very important. Another way of saying that is the information can never go beyond the speed of light. And that's also information. In a way, the information theory should then also know that as well. So, I don't know. Maybe I'm putting in that language is really more enlightening. I don't know about the theory of everything in any ways. But I think it is an important concept to always think about. Like, is that the spectrum of the theory that you're going to look into, all the particles? Or is that about something that's explicitly more measurable? Like, correlation function is measurable, I would say. Or entropy, like these things. Like, it's also individually some physical things that we can be understanding as explicit computable quantity that encodes some information. So in a way, to describe all of them requires different type of toolkits or different type of techniques. So in a way, that how we understand the information in space-time is basically physics of the universe.
When did you first learn about these connections between high energy physics and information theory approach? Is this something that you found out about and then you really wanted to dig into deeper, or is it something that emerged just naturally in the course of questions you were already interested in?
So I was a grad student, and there was a one semester that we decided to invite a lot of entanglement-focused researchers in high energy theory, of course, and they're making a lot of progress. But I was listening to a lot of these talks, and it was fascinating. So I started reading a lot more about them. And I mean, I'm kind of like a gravity child in a way that gravity is fascinating to me. I think in a way that I'm a high energy theorist in the end was because I really liked gravity and I wanted to understand better. And this technique sounds like God-given or very new. I should understand better. So I was looking into it, reading and studying them. And from some point, I realized that I think I can really maybe understand better and contribute in a way that the questions I want to understand better. So I started jumping in and working onto that field. I think it's been very good. It's been very exciting for me. I learned a lot of new things. So that's been very fruitful, I think.
And it is it's a growing field, right? There are a lot of people looking for these connections now between, I guess, all sorts of different aspects of physics. One thing that I did want to ask you, actually, you mentioned a few times CFT. So CFT is a conformal field theory, for anyone listening who's not familiar with the term. Can you briefly explain what is a conformal field theory? How is this different from any other type of field theory? What makes it special? What makes it useful?
So for a generic quantum field theory, it flows in the IR limit to a conformal field theory.
Okay, so the IR limit then, that's the low energy limit. Is that correct?
In some way. It's like RG flowed down, like renormalization group flowed down to CFT. So, I mean, it would be still somewhat high, but it's a lower scale, for sure.
So maybe not low in the sense of
like maybe
where
not
I
the
come
cold
from.
atom level, but...
Okay. And then conformal invariance, you say, is the lack of any distinguishing length scale, I guess. It's a theory that looks the same scale on all length scales. Why is this a useful concept?
So CFT is used heavily from way back in the days to understand a lot of things. Like 2D CFT naturally arises in a variety of condensed matter theory systems, understanding better, like topological phases and a variety of things. And also a string theory, like in the 10-dimensional theory, with supersymmetry can be encoded as string. So it's a world sheet can be arise from that, and that forms a world sheet conformal field theory in 2D as well. So in a way, like the whole thing is encoded in 2 dimensions and could be analyzed much better to lower dimension. There's no scale. A lot of things are directly computable. Physicists like explicit things that we can understand better. Maybe we see explicit identity or conditions, equality, most importantly. These are great, right? So CFT had been a great toolkit that can understand a lot of variety of things.
So there's a theme kind of emerging here about encoding the information about complex high-dimensional systems in, I don't want to say simpler low-dimensional systems, but let's say alternative low-dimensional systems that can be studied in different ways. This is a theme that's come out of several different things that you said here, and this, I guess, is why concepts like quantum information are useful, because they are properties shared by both of the theories. So by investigating the, in some sense, I guess, simpler low-dimensional theory, you're still finding out about these higher dimensional theories. You're still learning something about
gravity in a theory that would by itself be very, very hard to understand.
Right. Basically, what can we do to understand more difficult gravity is our grand goal. And we take anything we can do. Information structure is useful. It seems naturally arising, fascinatingly in the universe. We'll take it. We'll utilize the toolkit, understand better, and really do the analysis to understand more about the bulk gravity theory. That is always the best way we can do, in a way.
And does this correspondence go both directions? Does the quantum information and quantum technology community gain anything by having access to these gravity theories? Is there anything the gravity theory can tell us that we could take and apply to quantum technology?
I actually have no idea. That's a very difficult question. I always used a lot of quantum information theory for these type of research I did. I'm very happy about these informations and also operator algebras to encode these and all that. I don't know whether we gave back to your community of quantum information or even operator algebra. That's not a question that I guess know the answer to, but I hope we did. I don't know. But I think the focus here is that there is clearly the interface of two different fields that can talk to each other and learn better. I'm sure there's a lot of great physics that can come together. I think that's a very exciting phase that more collaboration can happen in this fashion.
Definitely. Touching on what you say there about collaboration, one of the great things, one of my favorite things I think about this career is that we do get to talk to people from all over the world, people from different institutes, and we get to move around quite a lot and go to visit other countries and other research groups. You've now, I guess you've worked in several different countries. You're based in the US at the moment and you're here visiting us in Berlin. Have you noticed anything different in the attitudes towards science in these different countries?
There are different techniques that's more built in different type of countries. The topics that they're mainly focused on does vary, I think, based on region by region. I think it makes sense. I mean, you talk to people more near your home, so people will be more working on similar fashion than not. But I'm also visiting quantum information group at Berlin, and I'm mostly in high energy theory group at Caltech. So maybe that is not as fair as a comparison, per se. But I'm enjoying my visit. So Berlin is a great city.
It is. It's a wonderful city.
Yeah. Wonderful food, too. And I also really like that when I'm visiting different places, I get to talk to different expertise of variety of people that work on slightly different focus. And that's very fruitful as a scientific collaboration. Because if you're just talking about the same thing and same people who agree with you all the time, I don't think it's going to go really as fast as a whole scientific community together. So I think that's having variety of different thoughts, different philosophies, different expertise and focus is very essential. So in a way, I guess saying diversity is very important in science. It's really unfortunate that we had to experience the pandemic, that we couldn't visit as much. But I think there's one thing that we really got out of it is Zoom. Things are so much easier to connect. Of course, it's not as good as in-person dynamics, but it's easier to now follow up after the visit and can get the discussion going.
So a diverse range of different perspectives then gives rise to fresh ideas and that drives progress.
I think so.
Touching on this theme of diversity, there's a question that I like to ask every guest on the podcast, which is that physics has historically not been a very diverse science. It's been largely driven by men, largely driven by white men for a very, very long time. Things are changing, I think, in the modern world. There's still a very long way to go, obviously. But I wonder, in your experience of your career so far, have you seen attitudes change? Have you experienced different attitudes in different countries?
Yeah, there's an overall difference. So as a woman researcher, it's been always rare to see another fellow woman. That's something that would be great to have, and more understanding of that would be great, because I'm sure different perspective is not just built in university. It's probably built in over the entire your lifespan. That's how you approach anything in life. I think that'll be very useful to incorporate into. I'm sure people are now trying more hard to see what would be the right way to include the diversity together. I know at least at Harvard, where I did my PhD studies, they have been thinking about it and in live discussions. So I guess that's a start. I think having BLM movement and Me Too movements would probably give something good in the end, that academia will be more open to everyone and can be accepting of more perspectives. I'm sure it'll be more fascinating in the future, so that it'll be better, faster, and new ideas. I think that'll be probably in progress. Yeah, I'm not a person who's in admitting or anything, so I don't know what's really directly going on like now, but I'm sure there's like a different overall directions that people are taking. So it'll probably lead to more diversity in science.
I hope so, because I think, as you say, that can only be a good thing. It can only lead to more ideas, to more discussion, and ultimately faster and better progress.
Mm-hmm. I think so too. I don't know. That one, to me, it's very obvious that more background in diverse ways will only help to foster a different way of thinking styles. And it's kind of a number game, right?
Yeah,
there are a variety of different ideas. Some will bound to work. And if that number increases, it'll be always better.
Would you have any advice for anyone looking to get into theoretical physics as a field? So perhaps someone who's in undergraduate or maybe like senior high school, maybe thinking about physics, maybe interested in physics, but not sure if they want to really commit to the career in physics?
I think it'll be good to read a lot of the things or listen to Stephen's podcast.
Thank you.
And there are a variety of outreach styles that people put a lot of more effort on videos, and I think science education videos are much better nowadays than when we were in high school.
Mm-hmm, definitely.
I think it'll be very beneficial to understand what's the interest that triggers as a high school kid or undergrad. And if you're undergrad already, there's a lot of faculties that they can go and talk to and try to see the feel, how the research is like, and take classes that they're interested in. I think it's more like you need to really go and learn things and try to see what's available to see if this is a right thing to do. Well, physics is awesome, so I don't see why anyone would not want to do physics. But that's probably what physicists will always say.
One final question to end then. I've asked you what advice you might give to someone else, but if you could go back in time and give yourself one piece of advice, what would it be?
I would have said, whenever you think it's very difficult and looks not possible, it will work in the end. You'll have to find another way. Don't stop trying.
I think that's a good note to end on. Well, if our audience wants to learn any more about you or hear more from you, where can they find you?
Well, I have a website. It's caltech.edu/squiggly-monica. Very easy. Or my email is monica@caltech.edu. Also very easy.
Yes, that's quite a remarkable email address that you have there.
I'm very proud of this. It's the greatest email.
Well, we will be sure to leave a link to your website and your email account wherever we put this podcast, so on our own websites and on our various other distribution channels. So thank you very much, Dr. Monica Kang, for joining us here today.
Thanks for having me.
Thanks also to the Unitary Fund for supporting this podcast. If you've enjoyed today's episode, please consider liking, sharing, and subscribing wherever you like to listen to your podcast. It really helps us to get our guest stories out to as wide an audience as possible. I hope you'll join us again for our next episode, and until then, this has been Insight Quantum. I've been Dr. Stephen Thompson, and thank you very much for listening. Goodbye.